this video, we are going to be talking about Williamson synthesis. So as the name suggests, it's used for the synthesis of ethers. I mean, the name part as in the synthesis part. Anyways, so this particular reaction is used for the synthesis of ethers. So the ethers can include, or rather it includes, symmetrical as well as unsymmetric ethers. So alkyl or aryl halides react with sodium alkoxide to give rise to an ether and sodium halide. So, alkyl or aryl halide react with sodium alkoxide to give rise to ether and sodium halide. That is a basic idea behind Williamson synthesis. So, let's look at the reaction. Rx, which is an alkyl halide, reacts with R-ONA to give R-OR-. R-OR plus sodium halide, that is NaX. So basically this and this is combining and getting removed, and you have R-OR. That is the ether formed. So let's do an example. For example, we have CH3 CH2Br, which is basically bromoethane, is reacting with sodium, and the alkoxide over here is ethane again, CH2. The carbon part, the alkyl group of the alkoxide is ethane, and this at 330 Kelvin forms CH3. So basically this and this is going to get combined. This part is getting removed. So CH3, CH2, O, CH2, CH. So this is a symmetrical ether. Now there could be, plus NaBr. So even ethers which have a substituted alkyl group can be synthesized using this method. So for example, CH3Br is reacting with sodium, oxygen, and then you have carbon, CH3. So this is a substituted ether which will be formed. So it leads to the formation of the CH3 stays the same, oxygen, then the carbon, methyl groups. So basically the lone pair of electrons will come attack here, this shifts here, and that's how bond is formed. Okay, now if you notice, in both these cases, wherever the alkyl halide was used, we only used a primary alkyl halide. Okay, but if we use this because primary alkyl halides give the best results for Williamson synthesis. So instead of a primary alkyl halide, if we land up using a secondary or tertiary alkyl halide, these are the reactions that you will observe. So in case of a secondary alkyl halide, for example, CH3 CHBr with a CH3. So this is 2-bromopropane. It is reacting with the sodium alkoxide. Okay, and this leads to the formation of two products. Okay, in this case, in case of a primary alkyl halide, we just had one product being formed along with, apart from NaBr or the sodium halide part. But in this case, we'll have two products being formed. One will be the substituted product, and the other would be the elimination product. So in case of a secondary alkyl halide, we are going to get both these products. So you will have propene, okay, and propene is formed as the major product, and that's 78% of propene is formed. And we also have the formation of the ether. So that is 2-ethoxypropane. So here we have the formation of 2-ethoxypropane, and this is a minor product. This is 78%. This is formed by elimination, while this is formed by substitution. So when an alkyl halide is a secondary alkyl halide, we are getting two products. One will be the elimination product, the other is the substituted product. But if we are using a tertiary alkyl halide like this one, Br plus NaOCH3, this will lead to the formation of only the elimination product, which is CH3, double bond CH2. Okay, here there is an elimination reaction taking place in the alkyl halide, and NaBr is formed along with the alcohol, methyl alcohol. So in case of primary alkyl halides, we are getting an ether, okay, because it's undergone substitution reaction along with sodium bromide or sodium halide. In case of a secondary alkyl halide, we are getting two products. One is an elimination product, the other is the substitution product. In case of tertiary, we are getting exclusively the elimination product and then alcohol. Remember, that's why we are using a primary alkyl halide for the Williamson synthesis, or for the synthesis of symmetrical and unsymmetrical ethers. Now the reason we have the elimination reaction taking place is because alkoxides not only act as nucleophiles, but they also act as strong bases. So when they react with tertiary alkyl halide, they are going to react as a strong base, and that leads to the formation of an elimination product. Now, this reaction can also be used for the synthesis of for synthesis of aryl ethers. Okay, so basically, okay, I don't have space. I'm just going to erase this part. Right. So basically, you have phenol. So phenol is also going to undergo Williamson ether synthesis. So it reacts with sodium hydroxide, forms sodium phenoxide, similar to the other two reactions that we learned about just in the previous two videos. So sodium phenoxide ion is going to react with an alkyl halide, and this leads to the formation of an ether. So this also, one moment, just for a second I thought it was not Williamson synthesis, I'm sorry. So when phenol reacts with sodium hydroxide, it leads to the formation of the sodium phenoxide ion, which on reaction with the alkyl halide gives rise to the ether. So this R group can be CH3, can be CH3CH2, it can be ethyl methyl propyl. Okay, so that's about Williamson synthesis. Basically, an alkyl or an aryl halide is reacting with sodium alkoxide to give rise to an ether and sodium halide. We remember, we will always use a primary halide for the synthesis of the ether, and this is because in case of secondary and tertiary, we start to get elimination products as well. In case of secondary, we have a major product, that's this one, which is the elimination product. In case of tertiary, we only have the formation of the elimination product, and we don't have the ether at all in case of tertiary. And phenol reacts with sodium hydroxide to form the sodium phenoxide ion, which on reaction with RX, that is alkyl halide, leads to the formation of the aryl ether. With that, we're done with Williamson synthesis. So in the next video, we'll be learning about Rosenmund reduction, which means we've finished with the name reaction for alcohols, phenols, and ethers. So do check it out.